All right, so next we'll have a quick look at some commonly occurring limits. This is called Theorem 5. The following 6 sequences converge to the limits listed below. The limit is n increases without bound of natural log n over n is equal to 0. The limit as n increases without bound of the nth root of n is equal to 1. The limit as n increases without bound of x to the power 1 over n is equal to 1 for any x greater than 0. The limit as n increases without bound of x to the n is equal to 0 if the absolute value of x is less than 1. The limit as n increases without bound of 1 plus x over n to the power n is equal to e to the x for any value of x. And finally, the limit as n increases without bound of x to the n over n factorial is equal to 0. And this is also true for any value of x. In these last 4 formulas, x remains fixed as n increases without bound. So feel free to use any of these. In a lot of cases, I think it's easiest to just find the limit, for example, by L'Hopital's rule. But that's up to you. Since we have covered it in a theorem, it's fair game for you to use and just cite this theorem. All right, another way to define a sequence is recursively. So far, we have calculated each a sub n directly from the value of n. But sequences are often defined recursively by giving first the value or values of the initial term or terms, and then a rule called a recursion formula for calculating any later term from terms that precede it. So this may be of special interest to you computer science majors because you define a lot of things recursively. So here are a few examples. In this first example, we're going to write out the first 6 terms of this recursively defined sequence. And then, assuming that each sequence converges, and that's kind of a big if that we're going to gloss over, find the limit of the sequence. First one, well, here they are. I'll have them written on the tablet. All right. So let's go ahead and switch over to the tablet. And we'll look at this first example where we are finding the first 6 terms of the sequence. First 6 terms. All right, well, the first term is given. The first term is 1. So now we have to find a sub 2. So using the recursion formula, a sub 2 is equal to a sub 1 divided by n plus 1. So in this case, n is 1. So that would be divided by 2. Since a1 is equal to 1, that means a2 is 1/2. a3 is going to be a2 divided by 3. 1/2 divided by 3 is 1/6. And I think a pattern is about to emerge from this. A4 would be A3 divided by 4. A3 is 1/6. When you divide 1/6 by 4, you get 1/24. You see the pattern yet? A5 is A4 divided by 5. A4 is 1/24. 1/24 divided by 5 is 1/120th. And then finally, A6 is A5 divided by 6, which is 1/120th divided by 6, which is 1/720. Okay, so even though they didn't ask for this, it's actually pretty easy to define this sequence explicitly, which is the way that we've always done it before, where, you know, if I asked you what is a sub 20, you could tell me what a sub 20 is just by plugging a 20 in somewhere. The pattern for this sequence is a sub n is equal to 1 over n factorial. All right, again, they didn't ask for that. I just couldn't resist throwing it in. All right, in the next couple of problems, this is where we are assuming that the sequence converges, which again is a big if. Assuming that the sequence converges, find its limit. Okay, so this is all you'll be asked to do in the homework. You won't be asked usually to show that the sequence converges. If you are asked for that, I will show you another tool that you can use for that under certain circumstances. So the way that I like to do these is, again, we get to assume that it converges. So suppose the limit of this sequence is L. Okay. Well, what would happen as you run through more and more terms of this sequence, and you get closer and closer to L, the terms of the sequence won't change all that much. And in particular, if you plug L in for a sub n in the recursion formula, you would have L plus 6 over L plus 2 is equal to L. Okay, so again, the value won't change. So that is the type of equation that you may recognize from, say, Math C. It is a rational equation. So I am going to multiply both sides by L plus 2. And that's going to give me L times L plus 2 is equal to L plus 6. I think this is going to be a quadratic equation. L squared plus 2L equals L plus 6. Subtract L from both sides. We're going to put this thing in standard form. That's going to give me L squared plus L minus 6 equals 0. We'll solve that by factoring. That factors into L plus 3, L minus 2 equals 0. So there are two possible solutions for L. However, I think we will be able to narrow down on one of them. If L plus 3 times L minus 2 is equal to 0, that means either L plus 3 is 0 or L minus 2 is 0, which means L is either -3 or 2. Now, I'm not saying that those are both limits of this sequence. A sequence can have at most one limit. In order to get an idea of which one of those is correct, let's look at the first few terms of this sequence, which I'm going to have to do over here, I guess. Okay, and I don't think it's going to take very many. A1 is -1. A2 would be -1 plus 6 divided by -1 plus 2, which is 5 over 1, which is 5. The next term would be 5 plus 6 over 5 plus 2, which is 11 over 7. And at this point, I think I know all I need to know, because it's pretty clear, isn't it, that this sequence is never going to go negative again. I mean, how could it? Once you reach A2, you get a positive number. And to get any term after that, you go positive number plus 6 divided by positive number plus 2, which is always going to be positive. So I think it's pretty clear that if this sequence converges, and I haven't shown you that it does, all right, it's pretty clear that it has to converge to 2. It is not -3. All right, next example. This is a fun one. So the sequence goes square root of 1, and then the square root of 1 plus the square root of 1, and then the square root of 1 plus the square root of 1 plus the square root of 1, et cetera, et cetera, et cetera. So it's helpful if you can write the recursion formula for this sequence. So let me just point out to you that the term A1 ends up here. The term A2 ends up here. So in general, what you're doing with this sequence, in order to get A sub n plus 1, you're just taking the square root of 1 plus A sub n. All right. So I'm going to use a similar approach to what we did in the last example. Suppose that this sequence converges and that the limit is L. Then in that case, it would have to be true that L is equal to the square root of 1 plus L. So now that's a radical equation. We also cover those in Math C. So I'm going to square both sides of that equation. And that's going to give me L squared equals 1 plus L, which is now a quadratic equation. L squared minus L minus 1 equals 0. And I'm sorry to say that I think we're going to have to use the quadratic formula to solve that equation. So quadratic formula with A equals 1, B equals -1, and C equals -1. So L equals minus B plus or minus radical B squared minus 4AC all over 2A. Hey. All right. So -1, which is 1, plus or minus the square root of 1 minus 4 times 1 times -1 all over 2. Oh gosh, where should I go now? I guess I'll go here. All right, so again, we get two answers, but I think only one of them could be correct. L is either 1 plus or 1 minus the square root of 5 all over 2. But just like in the last example, I think it's pretty clear that L has to be a positive number, right? Well, for one thing, all of the terms of this sequence are square roots, and square roots are always positive. Since square roots are always greater than or equal to 0, the limit has to be 1 plus the square root of 5 over 2. Fun fact about that number is called the golden ratio. And if you're interested in going down a mathematical rabbit hole, do a little bit of reading about Fibonacci numbers, because that golden ratio comes up with Fibonacci numbers. All right, so back to the presentation. It's fun stuff. All right, we're going to end by talking about bounded monotonic sequences. This is a lot simpler than it looks. Bounded means exactly what you would guess it means. A sequence A sub n is bounded from above if there exists a number m such that A sub n is less than or equal to m for all n. In other words, an upper limit on the terms of the sequence. Sequence will never exceed this number. Okay, that's called an upper bound. And similarly, a sequence A sub n is bounded from below if there exists a number little m such that A sub n is greater than or equal to little m for all n. That number little m is called a lower bound for the sequence A sub n. If the sequence never goes below that number, then that number is called a lower bound. If a sub n is bounded from above and below, then a sub n, the sequence a sub n, is bounded. If a sub n is not bounded, then we say it's unbounded. That's logical, right? So that takes care of bounded. A sequence a sub n is non-decreasing if a sub n is less than or equal to a sub n plus 1 for all n. So you see a word like non-decreasing and you think, oh, why can't they just say increasing? Well, there is a difference. Non-decreasing allows for some of the terms to stay the same. So I'll give you an example. The sequence 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, et cetera, et cetera, et cetera. That is a non-decreasing sequence. It wouldn't be correct to say it's increasing because it's not always increasing, right? Every other pair of terms, they stay the same. Okay, the point is that they're never going down. Similarly, a sequence is called non-increasing if a sub n is greater than or equal to a sub n plus 1 for all n. So that means either decreasing or staying the same. And finally, a sequence that is either non-decreasing or non-increasing is called monotonic. So basically the idea behind monotonic is that it's not going back and forth. It's either going up or staying the same, or it's going down or staying the same. It's not going up, down, up, down, up, down. Okay, that's monotonic. I don't think monotonic is a very descriptive word for what it is, because when I see the word monotonic, I think of the word monotone, somebody who talks like this, right? That would be a better term for maybe a constant sequence. It's not going up or going down. Okay, but monotonic means only going up or only going down, roughly. Okay, remember, we're also allowing for terms to stay the same. Okay, so what can you say? Oh, darn it, I have the answer right here. Okay, don't look, only look at the top of the slide. What can you say about a sequence that is bounded and monotonic? So it's trapped between two numbers and it's only allowed to go up or stay the same, or go down or stay the same. Here, let's do this. Okay, you're not looking at the middle of the slide, right? Well, I'm about to take it away from you. Okay, let me get over to a blank page here. Okay, bounded and monotonic. Let me draw you a picture of that. So suppose the sequence is bounded between this number and this number. So we'll call this big M, this is little m. And let's say that the sequence is non-decreasing. So maybe it starts here, stays the same, goes up, stays the same, goes up, stays the same, goes up, goes up. So my question is it possible to say that this sequence definitely converges, or is it possible that it diverges? Think about that for a minute. Well, eventually you start to see that one of two things is going to happen. Either the sequence is going to stay the same forever and never reach that upper bound. And in that case, the sequence converges, all right? I did not mention, you may have noticed it in the definition, but there's a difference between an upper bound and a least upper bound. So I'm not saying that big M is a least upper bound. I'm just saying it's some upper bound. So either the sequence is going to stay the same forever and try to avoid the number big M, or it's going to do some increasing and eventually it's going to get really, really close to this number M. And remember, it's not allowed to ever get bigger than that number. So what I am trying to tell you, because I know you didn't look, is that any sequence that is bounded and monotonic is guaranteed to converge. All right, so that is another way to show that a sequence converges, show that it's bounded, and show that it is monotonic. All right, so I have a couple of examples to end with. They're just asking which of the sequences converge and which diverge. The first one, a sub n equals 2 to the n minus 1 divided by 3 to the n. I think we could actually handle that one without using this bounded monotonic theorem. But letter B, this is a really interesting sequence. The first term is x sub 1 equals the cosine of 1. The next term is x sub 2, which is either x sub 1 or cosine 2, whichever is larger. And then x sub 3 is equal to x sub 2 or cosine 3, whichever is larger, et cetera, et cetera. In general, x sub n plus 1 is equal to the maximum of x sub n or the cosine of n plus 1. So let me switch over to the tablet. For letter A, I think you could have actually handled this example earlier because, again, I don't think we need this bounded monotonic business, but that's, I suppose, how I'll do it anyway. Okay, let's see. Is that how I want to do it? Okay, so I'm going to show this sequence converges, first of all, by convincing you that it's bounded. This sequence is bounded below by 0, right? It's pretty clear that this sequence is never, ever negative. And what's it bounded above by? Well, maybe if we look at the first few terms, the first term is 2 minus 1 over 3, which is 1/3. Second term is 4 minus 1 over 9, which is 3/9. The next term is 15 over 81. Term after that is 2 to the 5th is 32. 32 minus 1 is 31. 243. Okay. Well, you know what? We don't need a least upper bound. I think it's pretty clear that this sequence is bounded above by 1. And let's see, is it clear from that pattern that this sequence is non-increasing? I wanted to say decreasing, but I have to say non-increasing because there's actually no change going from here to here. Well, let's see. You know what? It might be clearer if we do it like this. Okay, so my claim is that this sequence is non-decreasing. Another way to think of a sub n instead of 2 to the n minus 1 all over 3 to the n is to write it as 2/3 to the n subtract 1 over 3 to the n. Well, 2/3 to the power n is definitely decreasing. And then if you subtract a number from that, you're just making it decrease even more. Okay. So, yeah. So I think it's pretty clear that it is non-decreasing. Therefore, this sequence a sub n converges. Okay, now this is actually not my favorite way to do this problem. I would rather just take the limit of this thing. I mean, hopefully it's pretty clear, especially when you write it like this, that the limit as n increases without bound of a sub n is equal to 0, right? Because 2/3 to the power n is approaching 0, and so is 1 over 3 to the n. Okay, so I would rather do it like that, but I wanted to show you how you could use this theorem. Now, I'm definitely going to use the theorem for this problem. So this is a recursively defined sequence. So we get to show that one of those actually converges. Oh, spoiler alert, this one does converge. Now, is it clear that every term of this sequence is a cosine? All right. The first term is cosine 1. The second term is either cosine 1 or cosine 2, whichever one is bigger. And I was looking at my calculator a few moments ago, and I found that, in fact, cosine 1 is bigger than cosine 2. So that would mean that x2 is still cosine 1. x3 would be either cosine 1 or cosine 3, whichever one is bigger. Cosine 1 is still the biggest. And in fact, cosine 1 is going to be the first 5 terms of this sequence. The next time we find a cosine that's bigger than cosine 1 is the cosine of 6. So the point is that this sequence, because it's always a cosine, is bounded above by 1 and below by -1. All right, and now I'm going to argue that this sequence is non-decreasing. As you move from one term to the next, it's always looking at the last term and saying, okay, which is bigger, the last term or the thing that I'm looking at now? So again, if you look at the first few terms, the first term is cosine 1. The second term is either cosine 1 or cosine 2, whichever is bigger, happens to be cosine 1. The third term is either cosine 1 or cosine 3, whichever one is bigger, happens to be cosine 1 still. So the only, the terms of this sequence never get smaller, they can only get bigger, all right? Therefore, this sequence converges. Unlike the last example, I don't have a really firm hold on what the limit of this sequence is. I have a feeling it's 1, but I don't really have any idea how to prove that. Okay, so fortunately, they're not asking for the limit. They're just asking us to show that it converges. And that finally is going to take care of section 10.1, and we'll see you next time.